Hello and welcome to another episode of R Stats. Today we're going to talk about repeated measures ANOVA. So to begin, I'm just going to talk about a little bit about repeated measures ANOVA and some specificities about it. So first of all, what can it do? Well, what it can do is twofold. The first thing it would be able to do is assess mean scores under three or more different conditions or three or more different time points. In fact, those are both of the things that it can do. And the big key here is within subjects. We're looking at within subject variation across three different treatments, and that would generalize to both time and conditions. So when should it be used? Well, when you're interested in looking at something like that. If we're interested in, let's say, within subject variation of three or more different conditions, that's when we're going to use it. So you want to be able to utilize what it can do. So how does it work? Well, a very generalized description of how it does work. Essentially, we're partitioning the sum of squares just a little bit differently than we typically do in a between subjects ANOVA. In this case, we're doing it within subjects. So what we're essentially going to do is we're going to produce an F ratio, a little bit different. And the F ratio involves, we're going to be dividing the mean square of conditions over the mean square error. So, again, very, very similar to the between subjects ANOVA approach. So moving on, we do have a couple assumptions, that of which we will test once we run our data. But to list them before we do that, we're going to be looking at sphericity, which can almost be synonymous and equated to homogeneity of variance. And that would typically be tested with Levene's test. But in this case, we're going to have a little bit different of a test that I will talk about in a few. And we're going to also want to as far as assumption-wise, we're also going to want to have a continuous dependent variable, and with that, we're going to want to have a categorical independent variable. And the final assumption that we're going to want to look at is independent observations, which is very typical. And I guess I could mention too, another assumption would be that our test variables, that they follow a normal distribution. But if we have a fairly large sample size, well, not fairly large, but a little over 25 or 25, then we don't necessarily need to worry about that because of the robustness of the test that we're going to use. Okay, so moving on, like I typically do in my past videos, we're going to talk about a relevant research topic to the field of industrial organizational psychology. So in my case, I thought of three different conditions that I'm going to place my subjects in, and because of the repeated measures test, they're all going to experience each condition, and in my case, I'm going to design an experiment where we have high, medium, and low job complexity situations where I have them complete a task that would be a proxy of an equated complexity situation that someone might experience on the job. And with that, once they experience each condition following that, they're going to complete a JSS survey, a job satisfaction survey. And my hypothesis would be that a medium complexity job would result in highest satisfaction because it's not on one of the polar ends. And I wasn't basing that off on research, but more just an intuition in my case. So I produced some data for that, and we're going to bring that data in. But first, we are going to run some packages. And in my case, why are we doing a repeated measure for that? Because I wanted to use the subjects as their own control, and I'm interested in within subject variation. And we have three different conditions, so that would fit the picture for running a repeated measures ANOVA. So now we're going to go into my data here, or rather my syntax. I'm going to open up a couple packages that we need. And as far as this, we're going to open easy package, ggplot, multcomp, NLME, pastex, and reshape. And we're going to need all of these for the stats that we're going to run here. And then we're going to open Excel, and that's going to help us read an Excel package. Now in this line here, we're going to specify within this section of the syntax, where is my data located, and this is where it is located, and this is the name of the data. So we're going to bring that in, and we're going to utilize the read Excel package for that, and this is what we're going to call it. We're going to push it in there. Now that it's in, it looks like we have a little bit of a mistake here. For some reason, repeated measures data was not found. So what we're going to do is we're just going to import it a little bit differently here. Rather than using the syntax, we're going to pull it in from my computer. where, oh where is it located? It should be located in repeated measures ANOVA. There we go. And there it is right there. And that's our name there. We're going to leave that as it is. But as you can see, we have it broken down into wide format here where we have levels across the top, which I will talk about in a little. So let's bring that in. And you can see it produced the syntax here to bring that in. What it probably was is, I think we did not have a capital R here. R is very specific in what it wants. We didn't have a capital ANOVA either, so the name was just a little off. But moving on, if we take a look at the data here now that's brought in, now that we can view it, you can see it's in what's called wide format, where we have the levels of our independent variable across the top, low, medium, and high, as I talked about before. And then we have participants down here, and we have 30 participants. Okay. So now, for us to run this in R, we're going to want to have it in long format. So we're going to use the melt function to do that, which creates a molten data frame. Ooh, scary, I know. So what we're going to do is we're going to use the melt function, like I said, and we're going to call this long data. We're going to push that into there with the push button right there. And we're going to specify ID. Where are we pulling this from? Where's our subject base? And that's in the participant column, so we're going to label it as that. And now we're going to say, what's measured here? What are our three variables? In our case, high, medium, and low. So I'm going to specify that. And then we're going to create a new data frame. And let's take a look at that. As you can see, it is now in the long format as opposed to the wide format where we originally had our variables going across the top like this. Now we brought them down into a new column called variable and value, which is our dependent measure here. And in our case, it would be the measure of job satisfaction from the GSS survey. And we still have participant here. And as you can see, it's in a little bit of a funky order where it's now sorted by variable. So we have all the lows, all the mediums, and all the highs. So now we're going to create a factor. And we're going to want to make variable a factor because currently we have it listed as a numeric variable. So we're going to produce that. And now we're going to move on to the next step here. We're going to want to order it so it's just a little more digestible for us. So we're going to use the order function here, and that's going to specify that we want to order long data by participant. Let's see how it did it. So now we have 1, 1, 1, 2, 2, 2. As you can see, they're all experiencing each condition. And as we go down, you can see that it's sorted by participant. That just makes it a little more digestible. So now we're going to begin kind of trying to get a picture of what our data is like, what our data is like. So we're going to produce a bar graph. And that produces that there. So now we can just get a graphical depiction of what's going on. Just looking at intuition sense, using our naked eye just to look at what kind of trends our data has. Obviously, we don't want to make any huge deciphers from this, but as you can see, they're fairly similar, so we're probably not going to be expecting a statistically different result according to each condition, but nevertheless, we're going to move on. And as you can see here, we have a low, medium, and high, and that is specified by condition as far as our x-axis is concerned. Okay. Well, alright, so now we're going to move on and we're going to set some contrast so we can get a better picture of what's going on. So we're going to specify 3 different contrasts here, and we're going to push those into a variable. And each variable will represent the contrast that we specify. So we're going to run these 3 lines here. And that sets the stage for the contrast. And now we're going to want to take a look at the contrast here. And again, like I've said in past videos, there is the juxtaposition from negative and positive contrast. So, and as a rule of thumb, you want them to equal 0. So an easy way to double check that is viewing them by executing long data variable, and that allows us to view them here. And in line 38, I should talk about how cbind essentially combines the contrast into a sensical order for R to read it. So we're going to run the contrast function. We're going to specify the name of my data, and then we're going to look at what's our variable of interest here. In our case, it is variable, and then we're going to use the cbind function to create an ordered pair, and we're going to, again, plug our variables into here. So now we're down to viewing them, and as you can see, we're going to want it to add up to 0 when we go down. So if we look at this one, we're going to be combining, rather looking at the difference between high and low because we have negative versus positive, and because we have 0 here, we're going to ignore that for this next one. And the next one, we're going to look at high and medium, and again, that adds up to 0. Okay, now that we specified our contrast, we're going to run an repeated measures ANOVA, and to do that, we're going to create a model here called easy model. Then we're going to use the easy ANOVA function, which is a little bit more simplistic of a way to accomplish what we want to. And then we specify our data here. dv, we're specifying our dv, which is value. wid, that's going to specify our manipulated variable, which is our independent variable. And within, that's essentially talking about our manipulated variable as well. I'm going to correct myself. I refer to this as the manipulated variable, but this is actually specifying our population that we are interested in here, which is our participant in this column here. And moving on, now we're going to say true, and this just gives us a little bit more detail to report as opposed to using the default of false. And then we're going to specify type equals 3, and that means we're interested in a type 3 sum of squares model. Now we're going to view the model here, and I will talk about what this means in a little bit, but as you can see, we are going to be interested in this output right here, Mauchly's test for sphericity as far as assumptions are concerned. But at the end of this video, I will talk about what our outputs mean and infer what they mean. And I want to go back for 1 second just to correct myself. When I refer to the participant variable as our population, that wouldn't be the correct nomenclature, more so our sample in our case. But moving on, now we're going to create a linear model. And I kind of did this because I needed some of the output, which we'll see later, that is necessary for one of the stats that we're going to run. So here's our linear model output, and that just is a little bit different of a picture of what's going on here. Now we're going to run a pairwise t-test in the case that we did achieve omnibus significance, which I will talk about in a little. Then you would want to run a pairwise t-test to get a better picture, a more granular picture of where the significance lies. So we're going to specify our data here. What are we interested in? We're interested in the value. That's our dependent variable. We're going to insert the variable name again right here. And then we're going to talk about, hey, look in long data, please, once again. Now we're going to say paired equals true. And then we're going to do a p-adjustment of the Bonferroni correction. And that's what p-adjust is specifying there. And we're saying true here is because we want to run a paired t-test model. We're saying that the means are dependent in our case. False would specify the opposite. So we're going to run the pairwise comparisons here. And now in line 55, we're going to want to run a contrast to get once again a more granular picture of where our effect is. What is our effect size? Do we have practical significance in our case? So what we're going to do is we're going to create a function like I've done in the past videos, and we're going to specify that as R contrast, and then use the function, and we want to tell R here, hey, we want to plug in T and DF. We want to produce values for those, and then plug them into the equation that we specify. So here we have the equation right here, and that's where the plugin is going to happen. And then we're going to say print paste R equals R, and essentially what that's saying is we want to produce an output of the value of what this equation produces. So it looks like we ran that there. And then we're going to run an R contrast, and this is where the linear model came in, because I'm going to want to look at some of our output, which I will do in a second, to plug in here. Okay, so we're going to run both of those, and this is going to produce an effect size for us. And here our effect size is right there. So now let's go back and we're going to talk about some output. So one of our first productions of output, I guess, would be the summary stats here when we use the by function. And again, this just gets you a little bit better of a picture of what's going on generally. And as you can see here, in juxtaposition of the graph, as well as our summary stat output, we do have pretty comparable means. Call it 81, 80, and 77. I know I'm rounding, but again, just a general picture. And as you can see, they're pretty comparable, and we see that as well here. So moving on. We're more so interested, as opposed to contrast, we're more so interested in the easy ANOVA output here. So what we're going to want to look at here, do we have significance? We're going to look in this line right here, over to the F value, 1.05. What is the significance of that F value that we achieved? Well, we're looking at 3.56 to the -1. So we're going to move that over, and we have not achieved significance. As far as assumptions are concerned, we did run the Mauchly's test within that model there, and what we're looking at the p-value here, and we have not achieved significance with that. In the case of assumptions, a general rule of thumb, not in all assumptions, but you don't want a significance, which is a little counterintuitive, but in our case we don't have significance, so that does mean that we did pass the assumption of sphericity. So moving on, what I was interested in as far as the linear model output is concerned, if we move down to our plugin, I guess it would be easier to look at it on here. We said our contrast, and then we had a value here and a value here. In our case, 58 is the degrees of freedom, which I got from our linear model output. And we also have this value here, -0.43. So let's see where I got that from. As you can see here, we're looking at the t-value in the variable high versus low for that comparison. And then for high versus medium, to get the effect size, we're looking at the t-value here. So I'm taking both of those, -0.43 and -0.97, and I plugged them in to this here. And I also did include a couple more figures to get a more granular depiction. So that's where I got those from, in case you were wondering. So now we're going to look at the output of our pairwise comparison, and these are going to be p-values here. And it's kind of a strange depiction of it, but we're going to look at high versus medium, 0.59, 0.78, and 1.0. And this would make sense because we did not achieve omnibus significance. So as far as the pairwise comparisons are concerned, we would not expect any significance here, although we do have approaching significance there, 0.59, but nothing different about. And if we take a look at our effect size here, 0.057, fairly small, 0.12, also fairly small. So that is my experiment. Thanks for watching.